Hi, in this video I want to show a tool that I recently created to read data from and write data to an I2C target using your PC. I'm using Digilent Basys-3 FPGA evaluation board for UART to I2C translation since I thought that would be fun. I do realize that this probably would have been easier to do with a microcontroller. In this video, the I2C target is an EEPROM with 4 kilobytes of memory, but these tools that I'm going to show you would work with any I2C target. So I want to start off by walking through this block diagram for the block data write to the I2C target. So the communication starts with this write data file.py script that's reading data from the CSV file, and I'll show you that format in a little bit. Your PC then sends data over USB to this FTDI chip, which converts the data to UART, which then goes to the FPGA, and the data is finally converted into I2C. So I want to highlight here at the bottom of this page the UART send message format. And the first thing that I want to show you, or I want to highlight to you, is that the UART messages are sending ASCII characters. So for this 00 message that we're sending 2 UART bytes, where each byte is an ASCII character. And when the FPGA interprets those bytes, it's interpreting each character in hex, so it's only interpreting it as a 4-bit data, and that for that reason, 2 UART bytes is equivalent to 1 I2C byte. Great. So when we're sending this write message, the first thing that we want to send is 2 UART bytes where they're both 00, and this will tell the FPGA that we're going to be doing a write operation, which it will then handle differently than if we were going to do a read operation. After that, you can send the I2C target address, and the FPGA will know to send the read-write bit as 0, since you already told it that we're going to be doing a write operation. Then you can start sending your I2C data bytes, and you can send up to 100 total UART bytes, or 50 of these I2C bytes, and then your message has to be terminated with the uppercase Z to let the FPGA know that you're done sending your UART message. This is all, of course, going to be handled for us in the tool that I'm about to show you. But one other thing that I wanted to show you real quick is that in the example today, we're going to be writing data to specific addresses in the EEPROM target. And the way that we do that is by these first 2 bytes being used as the address bytes. So this would be the most significant byte for the address, and this would be the least significant byte for the address. But not every target needs that. And the backend functions that are being used by this write data file.py script could send data without the data address if that's what's needed by your application. Great, so let's actually run the script. I'm going to open up the logic analyzer just so you can see the communication going on in the background and the terminal. So I'm already in the right directory. I'm just going to run Python write data file.py and pass as an argument this test write data.csv. Great. And so real quick, I'm going to show you the format for the CSV. So this is the CSV, just opening it in Notepad. And the Python script just expects every line to have 1 byte. So here you can see that every byte is AA for all 4 kilobytes. Yeah, and it's 1 byte per line, 2 characters per line. So while this finishes running, it's going to take about 30 seconds. I also want to show you the circuit for the I2C that the FPGA is connected to. Since the FPGA only has digital inputs and outputs, and I2C is an open drain protocol, we needed to do something a little bit more sophisticated than just connecting 1 pin from the FPGA to the data bus, or to the data and clock buses. So the way that I work this out is that we have 1 data input that is connected directly to the data bus, and we have this data output which is connected to a BJT, although we could have as easily used any transistor. So the way this works is that FPGA data out, when this goes high, the BJT is conducting, and so the data bus is pulled low. When this data out is low, the BJT is not conducting, and so there's no effect on the data bus. And that gives us sort of the open drain effect or I guess in this case the open collector that you need for I2C. And the same thing is uh, done on the clock side as well. We have this clock input that I'm not using yet, so in this implementation there is no clock stretching being done, but I'm going at such low speeds that there doesn't need to be clock stretching for this target. Great, so let's take a look back at our logic analyzer and we see that the communication is done. So now we want to verify that. But before we verify that, I'm going to show you the block diagram for reading from the I2C target. So it's all the same blocks from the right block diagram, but now you can see there's communication going in both directions. So you're going to send a UART message and then you're going to receive a UART message. At least that's how it's going to appear to the Python script. Great, so I want to talk about how the UART send message is a little bit different format when you're going to be reading. So now you're going to be sending 10 bytes over UART no matter what. And these bytes are going to be these functions right here. So the first 2 bytes are going to be FF to indicate to the FPGA that you're doing a read. You follow that up with the I2C target address, and then you have to provide a data address here. So that will be the 2-byte data address, MSB and LSB, and then finally you tell the FPGA how many bytes you want to read. And then you terminate the message with the uppercase C character. For now, the FPGA will only do reads of up to 8 bytes. And then after it communicates with the I2C target, the FPGA will return back the data bytes from your I2C target, starting with the least significant byte and ending with the most significant byte. In the case that you ask for 8 bytes, it'll send back these 16 bytes. Again, of course, because every UART byte is 1 character, which corresponds to only half of the I2C data byte. Great, so let's see this in action. So I'll open back up the logic analyzer just so you can see the communication happening in the background. And we actually have this GUI for reading information from the I2C target. So I'll run python eprompt GUI.py. And one thing I do want to mention now is that there's the target address for the I2C target, as well as, for example, the COM port number and the baud rate for the serial port are all just definitions right now in the Python script. I decided to leave those out of the GUI because if you're working with the same I2C target frequently, then you wouldn't want to have to go change those every single time. But if you want to, those could be accessed in the source script for this GUI. So now we can input the data address. And so let's start off with, I don't know, FF, because it's 4 kilobytes. We can choose anything in that range. And the number of bytes that we want to input, we'll say 8 for now. You load the memory, and there it shows in the GUI. You can input as many bytes as you want. It will take slightly longer to read more bytes. Great. And so also, if you want to change a byte, you can just double click on the byte, input your new data, save it, and it's saved. If you want to load memory again just because you don't trust that it got written correctly, there, you can go ahead and do that. One more feature that I wanted to show is that you can actually click this continuous refresh button if you wanted to, for some reason, continuously read the memory over and over again. You can keep monitoring it to see if your data changes. Great, so I will provide the GitHub repo in the description of this video for anybody that wants to try out this GUI or the block write script, as well as I will be providing the source for the FPGA. And feel free to reach out if you have any questions. Otherwise, thank you for watching.